Hello guys, how you doing? Today is the first session of chapter 4. The title is the velocity field. So follow me with the whole video. So as I already told you, I'm going to instruct you the velocity field, which is from section 4.1 of chapter 3 of Fluid Mechanics 1. Before going on instruction, I'm going to introduce myself. My name is Amir Raza Talaqat at the email address of amirrazatalagat@gmail.com. You can just send your questions via the email address or just comment them in the part of this video comments. First of all, I'm going to read the text and I'll give you more demonstrations. In general, fluids flow, there is net motion of the molecules from one point in space to another point as a function of time. It means that when we have a fluid motion, we can just see that molecules are dislocating from one place to another. Furthermore, if we just take a look at the particles, there are million molecules in them. So we would much rather to go through the particles motion analysis in order to identify the velocity and the acceleration of the fluid, because it's more easier to do. At a given instant in time, a description of any fluid properties such as density, pressure, velocity, and acceleration may be given as a function of the fluid's location. It means that when we are going to analyze the particle's motion, we have to regard the location or the position of that particle as well as the time that's passing by. This representation of fluid parameters as functions of spatial coordinates is termed as fluid field representation of the flow. So when we are considering the time and the location, it means we are just utilizing spatial coordinates. In definition, this utilization is named as field representation. Of course, the specific field representation may be different at different times, so that to describe a fluid flow, we must determine the various parameters, not only as a function of the spatial coordinates x, y, z, but also as a function of time. So we are just dealing with 4 parameters. 3 of them are regarded as coordinates, and the 4th is time, is the second parameter that we are regarding. Second most important that we are regarding. For example, the temperature. If we just want to identify the temperature field, we have to identify the positions, which are x, y, and z parameter, as well as the time, which is the t. The most important field that we're going to discuss about is velocity field, defined as this: u as x, y, z, t I hat, v x, y, z, t j hat, and w x, y, z, t k hat. It means that every parameter of the velocity field has to be coordinated by x, y, and z, and most likely the time that's passing by. As you see in here, we have the velocity vector. So in this picture, you're seeing that the particle's position is located from the coordinates at the origin by the vector of RA as a function of time. So the time derivative of this particle's location is going to give us the velocity at that point. As you know, as you already know, we are just regarding the particle's position. It means that we are considering as a vector. As a result and consequently, we are having it as the vector of velocity or the vector of the position are having the direction and the magnitude. So for example, the velocity, we are just denoting it as absolute magnitude of the v is u to power 2 plus v to power 2 plus w to power 2 square root of the total of them. And in this picture, you're just seeing a velocity field in more detail, the velocity vector that are passing across these two squares. So in order to get the concepts better, I'm going to solve you the example 4.1, which is about velocity field representation. So follow me with the written text of that problem solving. Welcome guys to this section, which is problem solving of example 4.1, the subject of velocity field, section 4.1, chapter 4. The question is to identify the location at which the velocity is equal to v0 with respect to this velocity profile. The second term is to sketch the velocity field for any location bigger or equal to 0. At the first step, as it's written, we have to figure out what's the magnitude of the velocity, which is based on this equation: u to power 2 plus v to power 2 plus w to power 2 square root. Doing the calculation, we'll have it as this: v0 over L multiplied by x to the power 2 plus y to the power 2 square root. In order to have the direction of any velocity vector, we can have it as this equation: the tangent of theta is equal to a v term of velocity over u term of velocity, which is v0 y over L divided by minus v0 x over L, which is minus w over x. Based on the triangular equations, we already know that this minus sign over here is indicating that every velocity field is toward the origin, and it's in the negative direction, which if we have it in the x direction, it is toward to the origin. And as the velocity is bigger than 0, we can have it toward the origin on this side, which is this or this. For the minus y, we can, because here we have a negative sign, minus to minus y, we can have it as this because the origin is indicated as this. It's already located in the figure that I'm going to provide you in a few seconds. Welcome back, guys. So we are going to the first section of the section 1 of chapter 4, which is about Eulerian and Lagrangian fluid descriptions. You know, guys, when we want to describe a fluid motion or flow motion, we can just do it by two methods. The first one is named as Eulerian method, in which we can identify the fluid motion governing equations as functions of space as well as the time by prescribing the necessary properties such as pressure, density, or velocity by utilizing the measuring devices located at specific locations. It means that we can just obtain the information about the flow in terms of what's happening at fixed point in space as the fluid flows through those points. So as I already told you, we're going to fix a measuring device here, and we just analyze every particle or any flow motion that's passing from this specific point at a specific time. As you see, there's a contour plot of a pressure field in here, whereby gray shading indicating the high pressure positions, like here. This picture is a flow passing a row of jet engine turbine, in which we are locating the high pressure positions. So the second method that we can identify the fluid motion through is named as Lagrangian method. All in here, either we are regarding the particle changes as a function of time and position, but I'm going to illustrate to you the position term in more detail. In the Lagrangian method, we're going to tag every single particle, and moreover, we're just analyzing that particle's motion individually at any instant time. Getting the chimney as an example in the figure 4.2, if we are going to utilize the method of the Eulerian method, we can just consider the point 0, and we can just see every particle that's passing from point 0 at any instant. And furthermore, we can analyze the particles passing through this specific point. However, on the other hand, if we just tag particles like this, and we analyze this tagged particle in every instant, we're just using the Lagrangian method. If we just use the Eulerian method, we can't just identify every parameter as a function of time, unless we just know the location of that particle as the function of time. If we are in the Lagrangian method, we can just identify the position of that particle unless we know the position of that particle as function of time. So in the Eulerian method, the time is a key highlighted point, as it's illustrated in here, and in the Lagrangian method, position is the key highlighted parameter. So there are so many examples that we can see the Lagrangian method application in them. For example, the X-ray optics, which are analyzing the blood flow in the arteries, or ocean waves in the oceanographies. In the industrial field, we can just see the application of Lagrangian method in the analyzing of pumps and the turbines. So One of the important things that we have to consider in the analyzing one, two, or three-dimensional flows is that how much they are applicable for us, how much of those information is required to have the problem solved. Take a look at this figure, which is the photographic flow of flows that are passing across a wing. We have to identify the system that we are using, whether it's a three-dimensional or two-dimensional or one-dimensional. In the two-dimensional, we can just regard each parameter that's less than others. We can neglect that, and this is also the same concept for the one-dimensional flow. Excuse me. In the previous chapters, chapter 2 and chapter 3, we have already discussed what is the steady flow. It means that passing the time, the property is not going to be changed in the duration. For example, the velocity. If the velocity is steady state, it is not going to change in the duration, although it's dislocating from a position to another. The unsteady flow is having the vice versa concept. It means that when a velocity is velocity field is flowing, a particle is flowing at a velocity field, by passing the time, the velocity property is going to be changed. There are some various unsteady conditions such as non-periodic, periodic, or truly random flow. We can just see their application in the faucets when we are just going to turning on the water to come out of the faucet. This could be manual, which means it's non-periodic. However, in the irrigation industry, we can have a periodic water supplement, which means on a steady periodic flow, as you see in the solenoids of the valves that are here. In the valves of iteration, if we want to have a periodic irritation, it means we have on a steady flow periodic conditions. As you see in here, this solenoid could be programmed. It's a more concept of industrial automation, but it's completely definable. So let me see if I haven't missed anything. Yeah, we're just in looking. Yeah. So in the previous chapter, we already got the concept of streamlines. Streamlines are the lines that are tangent everywhere, tangent to the velocity field if the flow is steady. If the flow is unsteady, the shape of a streamline is going to be changed. There is a concept, there's a definition for steady flow, that velocity vectors have to obey this equation, which means the tangent of the velocity field is defined as v, the y parameter of the velocity, divided by x parameter of the velocity, which is u. These two parameters, these two sides, has to be equal in order to obey the steady flow concept. In order to comprehend it more, I'm going to have a problem solving of example 4.2, which is about streamlines for a given velocity field. So follow me with the written text. So here we have example 4.2, which is about streamlines from a given velocity field of section 4.1 of chapter 4. Here we have to identify the streamlines for a flow, which is discussed in the previous example with the velocity profile of v is equal to v0 over L multiplied by minus x I hat plus y j hat. In order to do this, we have to indicate which are the terms of the velocity. Here we have the u term, here we have the v term. As is discussed in the previous example, dy over dx is equal to v over u, which is equal to v0 L v0y divided by L totally divided by minus v0 L divided by x, which is going to be consequently equal to y over minus y over x. Doing the calculation, we have it as integration of dy over y is equal to minus integration of dx over x. At last, we have ln y is equal to, excuse me, let me have it, yeah. ln y is equal to minus ln x plus c. Doing the calculation again, we have the xy equal to c, which every c has its corresponding figure, as it's going to be provided to you in a few seconds. Welcome back, guys. Here we have another concept, strict lines. It consists of all particles in a fluid that have previously passed through a common point. So we can just do it by photographing. It's a laboratory tool. We can just fix a camera here and see and take photos in the megapixel scale in order to identify how many particles are passing and what's their property, temperature, pressure, and etc. As you see in this figure, it's demonstrating the flow motion across a car body, and at the under of it we can just see how it's analyzed by Fluent or any other fluid mechanical software. Another point about a strike line before we go to example 4.3 is that if we have steady flow, straight line and the streamline are having the same concept. If we have unsteady flow, because of changing the shape, as I already told you, the streamline is going to be changed, as well as the straight line, because when we are taking the photographs, if we are having the unsteady flow, we can just see the strike lines passing from previous any corresponding previous point are changed by their particle before them, with their particle before them. So, in order to get a better concept and interpret it in a better way, I'm going to solve you example 3.3, which is about comparison of streamlines, path lines, and straight lines. However, path lines are located at this part. So, I'm going to have the example solved for you with the written text. So, follow me with it. So guys, here we have the example 4.3, which is about the comparison of streamline, path lines, and straight lines from section 4.1 of chapter 4. The question is, water flowing from the oscillating slit shown in figure E4.A produces a velocity field given by V is equal to u0 multiplied by sine omega t minus uy over v0 I hat plus v0 j hat. These are constants, v0, u0, v0, and omega. Thus, the y component of velocity remains constant as the v0, which is obvious, and the x component at y equal to 0 coincides with the velocity of oscillating sprinkler head, which is going to be u is equal to y0 sine omega t at y equal to 0. There are two terms to be identified. First is to determine the streamline that passes through the origin at t equal to 0 and t equal to p over 2 omega. T equal to 0 and t equal to p over 2 omega. The second term, there are three terms. The second one is to determine the path line of the particle that was at the origin at t equal to 0 and t equal to p over 2. So here's the 1, here's the 2, t equal to 0, t equal to pi over 2. And the last term, which is the third one, is to discuss the shape of the straight line that passes through the origin. So in order to have the streamline for a first part, we have to take it as a dy over dx is equal to v term divided by u term of velocity, which is v0 over u0 sine omega t minus y over v0, which is in a further step is going to be equal to u0 integration of sine omega sine of omega minus omega, this is this sine omega multiplied by t minus y over v0 dy equal to v0 integration of dx, which is gonna be u0 v0 over omega cosine of w multiplied by t minus y over v0 totally equal to v0 x plus c. Here c is the constant. At t equal to 0, we can have c as u0 v0 over omega at t equal to 0. Here's this, which is gonna be ending the total equation as x equal to u0 over omega multiplied by cosine wy over v0 minus 1. Let me just enhance the light of the, yeah, here's it. The next step is to identify for the t equal to pi over 2 omega. For that point, for that t, we can have it as, if we replace the t as pi over 2 omega, we can have the, instead of this, we can have x is equal to u0 over omega cosine w multiplied by t over 2 omega minus y over v0, which is going to be equal to u0 over w, just enhance it, u0 over w cosine pi over 2 minus wy over v0, which is at last is gonna be equal to x u0 over w sine wy over v0. Here's the first term. The second term is to take care of the streamline was what? Yeah, to determine the path line. Yeah, here we have to identify the path line. So we can have it as this, because the path line definition is, let me just discriminate this part. Here we have the equation of dx over dt and dy over dt. The dx over dt is going to be equal to u0 sine omega multiplied by t minus y over v0, and the dy over dt is going to be equal to v0. Taking the integration with respect to y, we have the y is equal to v0t plus c1. If we just replace this into this, we can have the dx over dt, as u0 sine w multiplied by t minus v0 t plus c1 over v0, which is going to be totally equal to minus u0 sine c1w over v0. Doing the integration we can have it as x multiplied by minus u0 minus u0 sine c1w over v0 multiplied by t plus c2. At time t equal to 0, we have x is equal to 0 and y is equal to v0t. For time t equal to pi over 2 omega, we have the c1 equal to c2 totally equal to excuse me, let me just minus pi v0 over 2 omega. For the C2, excuse me, this is for C2, this is for, no, let me just enhance it. I'm gonna write it here. C1 is equal to minus pi v0 over 2 omega, and the C2 is going to be equal to minus pi u0 over 2 omega. All in all, for x term, we have u0 t minus pi over 2 omega, and for the v term we have v0 t minus p over 2 omega. The path line that can be drawn by plotting the locus of x as a function of t and y as a function of t, values for t which are bigger or equal to 0, eliminating the parameter t from these equations, we can have y is equal to u0 over, excuse me, v0 multiplied by x. In order to show you the strict lines, the strict lines that passing through the origin, I'm going to provide you the picture in a few seconds. Here we have it. As you see, each particle that flows the origin travels in a straight line that its slope lies between plus or minus v0 over u0 as here. The particles that are passing through the origin at different times are located on different rays from the origin and at different distances from the origin, which indicates that the unsteadiness of the strict line is already varying in every instant, which causes the oscillating and sinus character provided as shown. Welcome back, guys. Here we have the third and the last concept of the fluid motion, path line. As I already told you, when we are just tracing a fluid motion, you're just considering the path line. It means that we have just picked an individual particle in order to trace it. It's nearly to the spit image of Lagrangian concept. So if we have a photograph here, a photographic tool here, such as camera, when the particle is passing, we can just see there's a path line for tracing if we go through more details of photography. So here's the end of this chapter. We have just already known the streamline, straight line, and the path line concepts. They are completely the same for steady flow. For unsteady flow, they are not the same, because the path line, it might be changing. The straight line it's obvious that's changing. Streamline, because of the shape and the size changes, it's changing. It's varying, and it's the end. So if we want to have a photographic tool here, we can just trace every particle. So in the first step, you have to identify what's the state of the flow. If it's a steady state, which is most frequent in the fluid mechanics that we are instructing, everything is the same. So don't worry about it. We are just considering the steady state fluid motion. Thank you guys for having me accompanied till this moment of the video. I'm really glad that I've been into your service. Please don't hesitate to ask your questions. I'm available. I try my best to give you the answers as soon as possible. And most importantly, please subscribe the channel in order to get the notification of upcoming instructional sessions. I bid you all farewell. Take care. Have a nice day and time.